5-axis functions in SolidCAM. I broadly classified it as functions for aerospace, functions for automotive, and functions for die mold and styling. In the first part today, we are going to touch on the first 5 options, that is multi-blade machining, turbine blade machining, frames for aerospace, trimming, and engine ports. And in our subsequent event next week, we're going to do tire molds, fine features in die mold machining using 5-axis, and conversion of 3-axis programs to 5-axis, super finishing using 5-axis, multi-axis drilling, and STL machining for styling and model making in 5-axis. Let's start first with our swarfing function, which we introduced in SolidCAM 2013. A very robust engine, needs pretty minimal inputs, ready to cut results quickly. You don't have to provide a lot of supporting geometries to it. And the tilt control is done automatically by SolidCAM. So what we're going to do now is I'm going to pick up a typical frame component, and I'm going to show you a few options of swarfing on that particular part. Okay, let's start. So it's not a full frame part as it belongs to a customer, so it's a small portion of the frame part. And what we're going to see today is swarfing for these 2 pockets. So if I now show you the draft analysis of this part, you can see that in this particular pocket, I have got a negative draft of almost 13 degrees on this wall, a positive draft of about 15 degrees on this wall. So there's a blend area happening between negative and positive in this part, and we have got straight walls over here. Whereas in this pocket out here, we have got almost straight walls and positive draft. So let's start first with the inner pocket, which has got some negative draft. I already have some programs defined, but I'm not going to use it. Sorry. Let me add a new swarfing operation. And in the geometry, I'm going to use what we call as an automatic strategy. It works almost 100% of the time. So let me pick up the swarf surfacing, the surfaces. The side surfaces, these are the ones that I'm going to swarf. And this one. So these are the surfaces which I want the tool to swarf out. Okay. And I need to define the floor. If I don't want the tool to go below the floor, then I need to define the floor surfaces. Now the floor surfaces could be planar or non-planar entities. So it doesn't always mean that the floor surfaces have to be flat. They could be also NURBS surface. So including the fillet and the bottom surface, these form my floor surfaces. Okay. I'll pick my tool, 12mm ball nose, and I don't have to define anything because most of the defaults work very fast, very safely. I want to machine the inside of this component, and in the link I would like to provide a lead in and lead out with 1mm height. I don't want it to rub any material while it is entering into the part and exiting the part. So I want it to lift out 1mm. Alright, we are ready, and I'm going to hit save and calculate. Okay, the toolpath is generated already for the swarf. So if I now run the HostCAD simulation, that's the tool. Okay, what you have to see clearly here is there are 4 walls. 2 adjacent walls are straight, and one is having a negative draft and the other one is having a positive draft. So the software intelligently is trying to position the tool in such a way that there is minimum change in angle when it's going around the part. Of course, it's not going to be much visible on the straight walls, but when it goes closer to the negative walls, for example, it's now traversing over the straight wall, and as it goes closer to the inner wall, you can see what is going to happen. You can go to the front view, because this side is the negative. So as it starts moving towards the negative wall, you can see that the tool is already starting to incline itself, so that by the time it approaches the wall, it has already got the angle, so that it doesn't do that sudden change of angle out here. It's done it in a very gradual manner. Okay, it's traversing on the negative, but now you can see what is happening on this side. Since it is approaching the positive draft of the surface, it's again trying to change its angle to have minimum change at the blending area. So you can see by the time it has approached the blending area, it has already maintained the angle needed for that particular face out there. Okay. So it's cutting that area, and as it approaches this side, now this side is straight, so any angle here would work, so it doesn't change the angle so fast. As it leaves the corner, that's when it starts slightly moving out from the angle. So it's pretty much smart enough to understand when it is approaching a wall and when it needs to change the angle. Right, so we did our first pass. Now let's look how it would look on the machine. Let's run the machine simulation. I have a head type gantry machine wherein we have got the A-axis and the C-axis, and let's go line by line. It might not be very smooth on your screen because since we're using GoToMeeting, you could have some delays in the screen appearing on or the moves appearing on your side. It could be in it could not be very smooth. So what I'm going to do is I'm going to stop at each corner so that you can notice how the machine tool looks like, or the position looks like in A and C. It's changed itself. The C is rotated. Okay. Now that's the negative draft. And as it comes to the positive, it's changed itself. It's still using positive and negative again. It's straight. Done. So it's pretty fast. It did not require any tilting geometry. It did not require any supporting geometries. Just select the surface, calculate. Now, if I go back to my toolpath, now what it looks basically is you have got a single toolpath, but sometimes since this is an undercut, you could have a lot of material remaining, because if you have done a 3-axis roughing, you could have a lot of material, so you don't want to remove this swarfing in one pass. You would like to have multiple passes. So what I'm going to do now is I'm going to edit the toolpath, go to roughing, and I'm going to put 5 layers, pattern layers, with distance between each layer as 1 millimeter, and run a calculation. Okay, now if I look at the toolpath, this is how the toolpath looks like. I have taken multiple passes into the material, not allowing it to take one single pass, but I've taken more than one passes to gradually remove the material from the walls. So you could also put roughing passes both depth-wise as well as in Z. So you could put both these passes. So if I have to put it in Z, I'm just going to edit this. I'll go again to roughing and more, and instead of number of slices 1, I will say I want 10 slices, or I could even say slice distance of 1 and I could have more than one slices. So let me calculate 10 slices. Okay, that's also done, and you can see that it has calculated 10 slices, morphing between the uppermost edge and the lowermost edge, and also generating roughing passes stepwise. So it's done a pretty neat job by giving just minimum inputs. Okay, now let's look at the next one, the next pocket where we're going to do the swarfing. I'm going to copy this operation, paste it, edit, and I'll switch off the roughing because we don't need, I just want a single pass. Also a single pass here. But the geometry here is going to change. So I'm going to use the side walls, including the small surface out here. And like we selected the floor surfaces, I'm going to select the floor surfaces, including the fillets out here. Okay. Right. This is how, and that's it. Okay, so all my surfaces are selected. Perfect. I'm just going to run the calculation now. Don't need to do anything else. Right. Now let's look at the toolpath. So that's the start. That's nice. That's nice. It's okay. That's also okay. But I have a problem now. As it starts moving forward, you can see that it's changing its tilt to a very funny manner, traversing over some geometry and then becoming straight again. And then again, as it approaches the straight wall, there's a big change in its tilt. And then becoming straight and continuing on to do a better job later on. But this is going to be dangerous for me. It's going to be catastrophic on the machine if they are going to have so much of tilt. So swarfing also allows you to control this. Although it's almost automatic, you could get into situations where you don't like the tilt and you would like to control the tilt. So in such cases, I'm allowed to define tilt lines. So I'm going to pick edges of this part as my tilt lines. So I'm picking only the corner lines because that's how I want my tool to be oriented. I'm not going to pick any other line other than the edges. This edge out here. This edge out here. I'm going to reverse it. Okay. Reverse this. That's it. So I've got 8 lines that I've defined as my tilt lines. And I'll just hit save and calculate. All right. Let's run again the simulation and see what change has happened to my toolpath. And you can see that it's perfectly following the tilt lines that I've defined. Yes, it's not doing all those funny movements out here, including here. It's nicely following the tilt, following the tilt, following the tilt, and that's it. So what swarfing in SolidCAM allows you to do? If I summarize this, it allows you to pick an automated way of creating toolpath, and if the results are not to your liking, if the tilting is not to your liking, you can also control it using your own tilt lines. So you could have automation as well as control on the entire toolpath. Right. Let's move to our next application. I'm done with swarfing. I'm going to move to another application called the multi-blade machining. Now this was introduced in SolidCAM very recently in the 2013 version, and it makes the machining of impellers and blisks very easy. So let me open a file. Sorry. Let me open the multi-blade file. So it makes generating toolpath of parts like impeller with splitters, 1, 2, any number of splitters, or without, much easier than what it was before. It was not that these parts could not be machined in SolidCAM before, but the amount of input that was needed, the amount of construction that was needed to generate this toolpath was enormous and pretty lengthy. Now it's almost like a 3-axis toolpath, where you just pick the geometry and ask it to calculate, you have the toolpath. For example, in our multi-blade, we have got roughing, or scooping out the material, blade finishing, both the main blade as well as the splitter, hub finishing for the floor, and the fillets. Because majority of the times in impellers, your fillets are generally variable radiuses, which need to be finished separately. They have to be treated as a separate entity. Let's start with roughing first. The geometry I'm going to pick here is this one. The main blade, the splitter, and the other blade. So there are 2 main blades and 1 splitter, including the hub and shroud. My hub surfaces, so if I show you my hub surfaces, it's basically a small piece of surface out here. I have not even selected the hub surface right under the blades that I want to machine, but I've selected the hub on the adjacent area, just to show you that SolidCAM needs only a piece of the hub surface. It doesn't need even the hub surface to be complete, because it understands that the hub is a revolved surface and all it needs is one small piece of it, so internally it will generate its own revolved surface of the hub. So this particular hub surface need not be under the blade. It could be underneath some other blades, which are on the other side of the impeller. So it's not that they need to be exactly underneath it. And then you have the shroud, which is basically this small piece of surface. You need to just pick on one of these blades. You can either pick it on the main blade or on the splitter. Any of that is fine, because again, SolidCAM understands that it's a revolved surface and it does the surface of revolution for the shroud. So what I'm going to do is I'm going to create a toolpath which is an offset between hub and shroud. I'm going to leave a stock of 0.35 both on the blades and on the hub, so that for my finishing gets some material. I'm going to use a tool of 12 millimeter. It's a taper ball nose. The advantage here is basically that you get a robust tool with a small corner radius, and it's generally used for machining impellers. It's pretty common to use a tapered ball nose. Right. The clearance is set to auto detect, which means that you don't need to do anything. Just select the auto detect and it'll do it by itself. In the toolpath parameters, I have a maximum number of layers set to 10 and a maximum number of layers along the slices set to 10. So you're going to have 10 depths and 10 slices. Between the 2 blades, you're going to have 10 slices, and depth-wise, you're going to have 10 passes. Tool axis control is again default. You don't have to touch it unless and until you really want to control some things here, because the default works pretty much safely. Link also is set to automatic. You can see most of the things in multi-blade are automatic, unless you want to open them up and start playing up with those parameters if you don't like certain results. Okay, let me save this, and I'm going to calculate this toolpath. We've done almost 70 to 80% of the calculation. That's pretty fast. Right, we've done the roughing calculation, and if I run the host CAD simulation, you can see that the toolpath is already calculated. Very neat and clean roughing of the impeller. If I run the machine simulation, because I also want to show you some issues with the toolpath and how we can control it by editing certain parameters. So I'm going to go into my machine simulation. So I have a DNG DMU60T out here, and I'm going to switch off the toolpath and slowly run the simulation. I'm running it a bit fast because I want to show you some problem. Okay, I've stopped the simulation because I found a problem, and the collision is reported out here. You can see that I'm having a collision between the head and the bed because the angle, the tilt has gone beyond a certain degree, which has made the head go and collide against the bed. Looks nasty, but we need to fix this. Now, because most of the parameters inside were automatic, doesn't mean that you can't control the toolpath. You obviously can control the toolpath, and you can control it very easily. So we now need to fix the limits of our toolpath to suit the machine. So what I'm going to do is I'm going to go back into my toolpath. I'll go into tool axis control, and I have a parameter called machine angle limit out here. I'm going to use the machine angle limit and control it, let's say, to 92 degrees. What I'm telling to SolidCAM is the machine can at the most tilt to 92 degrees. So you have to keep your toolpath within this range, and hit my calculate button again. Okay, calculation is done. Let's run the simulation again. Right. Let's run it slowly. I'm going to run a few lines slowly so we can have a look at what is happening. Okay. What I'm now going to do is I'm going to run the simulation fast so that we will only check quickly if there is an error in, again, like what we had. And if you want to check how the multi-blade looks like after it has been roughed out, this is how it will look like. After it has been roughed, that's how the multi-blade looks like. Okay, let's go back again to our machine simulation. It's still running. Maybe I have to increase the speed a bit. And as you can see, I really don't have any gouges now because the angle has now been controlled to maximum of 92 degrees so that the head will not tilt beyond 92 degrees, and thereby it will avoid this kind of situation where it goes pretty close to the bed. So having automation, SolidCAM has not compromised on the flexibility to the user to control the toolpath. Right. Once we are done with our roughing, What we're now going to do is we're going to finish the blade, one of the blades. So I'll edit my next toolpath and I'll show you the geometry that I've selected. I've selected the entire blade along with the shroud as my geometry to cut, including the bottom fillet. Now remember that the most critical part of programming happens when you have selected the bottom fillets, because it's very difficult to control the tool axis when you have also added the fillet at the bottom. But you could see how easily SolidCAM handles this. So I have the hub surface and the shroud again. The tool remains the same. I'm going to take 15 passes on this particular blade, and I'll hit save and calculate. I don't have to define the tool axis, what is the tilt, nothing. Just select the faces, select the tool, define the strategy, and calculate. All right, the calculation is almost done. Let's run the simulation again. And let's look at this toolpath inside the machine simulation. I'm going to hide the machine body, and you can look at how the toolpath looks like. Pretty much smooth, nice roll on the front fillet, because the quality of the toolpath can be made out by these rolls that happen on the front side of the fillet. In many cases, you will see the tool dancing on the fillet, but in this case, it's pretty much smooth. No much input was needed. All that we did was define the surface, define the strategy, and calculate. So not much of a sweat on that part. Okay, let's look at the roll. Very nice roll. That's how it's going to machine. Nice. Okay, let's come out of this. We'll also do the same thing. We'll also finish the splitter. I already have the splitter surfaces and the hub and fillet. I'll just hit calculate. I don't need to define any kind of geometry other than the surface to be machined, just like you would be doing with the 3-axis toolpath. Let's run the host CAD, so it's much more easier for us. Okay, that's how the toolpath looks like. Again, it looks very nice, smooth. No much inputs, just the surface, tool, strategy, and it's all done. Right. Let's also now look at how we finish the fillets. I would now like to finish this fillet out here for the main blade. So what do we have here? We have the entire surface is again selected, including the fillets and the main blade and the hub. These are the only two elements that I need to select in multi-blade fillet finishing. And what else I have done, if I look at the toolpath parameters, I can define two types of cut, one on the blade side and the other one on the hub side. So I have 8 cuts on the blade side and 5 cuts on the hub side, and the distance between each cut is set to about 0.3 millimeters. Let's calculate this. Okay, that is done. Let's run the simulation. You can see pretty nicely it has put cuts from the hub side and cuts from the blade side. Very nice tool, very nice toolpath with minimal inputs. the tool axis, and all those things have been controlled automatically by SolidCAM. Let's do the same thing for my splitter blade. Calculate. Right, that's also done. Let's run the simulation. Okay, very nice toolpath even for the splitter, with both the cuts coming from the blade side and the hub side, thereby finishing up the fillet at the bottom. Okay, what remains now is the hub to be finished. So if I edit, you can see that the geometry is again blades, splitter, and fillets, and the hub. I've kept about 150 microns from the blade and the splitter because I don't want the tool to touch these areas when it's finishing the floor. And I've asked 18 cuts just to show you how the flow works. Calculate. Right, that's done. Let's run the host CAD out here. Very nice. See that the hub is now done. So you can see how quickly and easily multi-blade parts can be programmed. You could have a splitter or you don't have a splitter, it doesn't matter. The programming will be at the same pace, very easy, absolutely low inputs, and most of the things done automatically by SolidCAM. Right, let's move to another area, another very interesting area. Of course, here I would be showing you the general function of SolidCAM, and that is on turbine blades. So let me open a turbine blade out here. So I have got my turbine blade, and there are three things I'm going to show you. The first is machining of the main blade itself, the what we call as the aerofoil area, and then machining of the flank one and the other flank. It's going to be done on a 5-axis DMG machine. So let's look at, first of all, what we have for the main blade area. We have used what we call as a morph between two adjacent surfaces. So what it is going to do is, it's going to create a pattern that is morphed between this surface and this side. So it's going to morph between these two surfaces. What I also have done basically is I'm using a 16R, a 20R3 bullnose tool. So I'm not going to use a ball nose, but I'm going to use a bullnose to finish this particular surface. And since I'm using a bullnose, it's not a great idea to go flat on the surface. So what I've done is I've given a lag angle of about 15 degrees for this. And we're going to generate a spiral kind of a tool path. But the challenge is out here. Because my because my surface here has got a great undercut, when I'm machining the surface, I need to be very careful about this. So what does SolidCAM offer here? SolidCAM offers some gouge check options. In fact, it offers 4 different types of gouge checks. You can set different reactions to different surfaces. For example, for this surface out here, I have told SolidCAM that whenever it finds a gouge, it needs to push the tool away in positive X. That's how it's going to do. It's going to push the tool out in positive X to such an extent that it just avoids the gouge. And I need to check, I've asked SolidCAM to check the tool tip and the tool shaft. For the next one out here, that is for this surface out here, I have asked SolidCAM that whenever it finds a gouge on the surface, it needs to push that tool away by X minus, because it's on this side, so it has to be pushed in X minus direction. And the main surface itself that we are cutting, I want the tool to retract in its tool axis direction when it discovers a gouge. So that's all I need to define, and we will hit save and calculate. It's now finished the calculation and converting all the cuts to spiral. Once the spiral is done, it's running the collision check. And we have a toolpath. Let's run the simulation to see how first the toolpath looks like in terms of quality. Let's switch off the tool for a moment so it's much more easy. Okay, the side looks fine. The side also looks fine. Great. Let's look how it looks like in the machine simulation. Okay, let's go to the toolpath display to the tool number. Okay, and let's move slowly so that you understand what is happening. And you can look at the lead-in that I've provided. I've provided a vertical entry, vertical tangent entry into the material, so it gradually enters into the material, not provides a sudden entry. That's nice. And I'll show you the 15-degree lag. You can look at the difference between face and the surface. Now, if you analyze this angle, this is about 15 degrees, and this is the lag. I don't want the tool to be touching on the entire face, but I would like to be using only the front side of the tool to cut this part. So if I look from the front side of the machine, and if I switch on the entire machine components and start machining it slowly, sorry. So you can look at how nicely and easily the machine is cutting the part. The motions are very fluid. Every aspect has been controlled. The tool is having the lag angle. You're using a bull nose to cut the tool. It has been checked for gouges against those two areas, and it continues on. All right, let's come out of this. I now would like to generate this side. So what I have here, I've got what we call as a parallel to curve, wherein this is my curve that I'm going to use. I'm going to go parallel to this, and I'm going to just cut one pass for this particular face out here, and then provide multiple passes on this, on these faces. So let's try and run this calculation. Okay, that's done. Let's run the simulation now to look at how this toolpath looks like. Okay, the toolpath looks something like this. Let me again go and switch on the color of the toolpath. Okay, and let's go to the front, because that's very interesting to see the front side on how it behaves when it's cutting the tool. Okay, let's switch off the toolpath and run line by line. you can see that as it starts cutting, it's actually moving, or it's like sticking to the surface to which it needs to be parallel to. It's cutting it very nicely. Fluidic motions. Smooth. Nice gradual change of angles. Nicely smoothing. So you can look how easy it is even to program parts as tough as this turbine blade, and that too without having any dedicated application. You're using the general 5-axis functions of SolidCAM to program this part. All right. Let's do the same thing, but for the other side of the flank, out here. And we are using the same principle, like what we did for the other flank. Just calculate this toolpath. Since this side is almost straight, there's not much of a challenge for calculation. If we run the simulation now, okay, let's go to the front view. Switch on the toolpath and run it line by line. So there's not much of a challenge to this because it's almost a straight flank. It doesn't have much of negative angles coming in. Right. Good. So we have generated quickly the toolpath for the main aerofoil and also for the flanks, which are critical when you're machining a turbine blade. Right. Let's look at another application now. This is moving out from aerospace and entering, you could say, half into aerospace and half into automotive. Let's see how we cut ports, engine ports. Let's open, sorry, to open the code file, not this one. I need to open the port. Yeah, that's it. Okay, let me switch on the actual port data with me. So this is the port that we are going to cut. For a purpose of better visualization, what I've done is I've created a copy of these surfaces so that I don't really have to look at all this entire geometry. I can switch them off. I don't really need to see them. And I can simply work with simple surfaces and not look at the entire model. Right. So what we have in SolidCAM. In SolidCAM, we have a dedicated function that was launched recently with 2013 version for machining ports. So what do we have in port machining? We've got roughing, rest roughing, spiral finishing, and plunge finishing. And like multi-blade, this function is also totally automated. For example, I want to cut roughing of these surfaces. What I've done is I've split. I'm going to cut this side and I'm going to cut the other side because the other side has two tubes and this side it's blend between two tubes to one tube. So I've just segregated this area into two areas. So I've got the surfaces that are marked now. These are ones that I'm going to cut. The tool I'm going to select is basically a 16 diameter lollipop ball nose. Right. Select. Levels, not worried much about it. It's just a retract of the tool. I've created an imaginary cylinder that's parallel to x-axis with a radius of about 200. In the toolpath parameter, I'm having a maximum step over, like you do in roughing, of 5 mm and a depth of cut of 2 mm. Tool axis control, you can see, is automatic. You don't need to break your head on this tool axis because it's done completely automatic inside SolidCAM. Linking is also automatic. What we have to simply do is, once we have selected the path surfaces, and of course in sorting, I need to tell whether it's the bottom side or the top side. Now, wherever my coordinate system is, that side is my top side, and the opposite side is always the bottom side. So this is the bottom side. This is the up side, and this is the bottom side. Okay. So I want it to go maximum from the bottom side, and let's hit save and calculate. Right, it's done the calculation. Let's run the simulation. Let's first quickly see how the toolpath looks like. It's pretty nice. Let's run the wireframe and see how the toolpath goes up to. It's pretty nice, straightforward calculation. But now if you actually run in the with the tool, you can see what is happening actually out here. SolidCAM treats this port as a positional machining and tries to maximize 3-axis cutting as much as it can till it reaches a point. For example, now if I run the machine simulation, you're going to see this machine on a Hermle C30. I'm going to switch off the outer, and this is my port. So if we start looking at the machining, you can see that it's handling it like a 3-axis machine or 3-axis machining. Just positioned itself, and it's trying to go as much as it can. It tries to go deeper, but at a certain point, it realizes that it no longer can do a positional 3-axis machining. So what it does, it immediately switches over within the same toolpath and starts doing 5-axis, as you're going to see here. Stopped it, it's done, and it starts moving in 5-axis. Start moving in 5-axis. So it's pretty intelligent. It understands that it can maximize the roughing by using 3-axis, and then it starts moving in 5-axis wherever it just can't do any more 3-axis machining. So it's pretty intelligent in that way. Right. Let's also do the same thing for the 2 ports out here. The only difference is that we have selected these as our machining surfaces, and these are check surfaces. So I'm going to select the next 2 and calculate. It's finished one cube. It's going to the next one. All right, now let's look at the simulation of these. Also go into the machine simulation. Okay, switch off and run it slowly. even here you could see that it's maximizing the positional 3-axis machining. As much as it can, it's going to enter in 3-axis. It's going to reach a point where it no longer can do 3-axis machining. So what it basically does, it switches over to 5-axis simultaneous. So that's how intelligently SolidCAM works in machining the ports. So you can look at how it's doing. Right. Once we are done with roughing, I'd like to show you the finishing strategy also. Let's edit. Again, we have got the machining surfaces. I've just selected this tube for finishing, and I'm going to use spiral finishing with the same tool. And in Toolpath, I'm going to go maximum from top. Tool axis control, not needed. Link, not needed because it's all automatic. Just hit save and calculate. Okay, let's run the simulation. Let's stop this and show it to you directly in HostCAD. So if I show you the wireframe, this is how my finishing toolpath looks like. So as you can see, it's very simple, very straightforward, at the same time very powerful. Simple interface and very powerful functionality to generate toolpath without giving any much input for this particular function. All right, that was a bit of ports that we have. So we can machine ports, we can machine multi-blades, we can machine turbine blades, we can machine frame components for aerospace. What remains now is the last part of our webinar this week, and we're going to see some 5-axis trimming function for vacuum formed parts. So I'll open some part for that. Okay, let me switch off all these lines because we're going to use them later on. Right. So I have got this part where I need to do the trimming all along its periphery. Now, we can do the trimming in 2 different ways in SolidCAM. The first was the one that we already saw in the aerospace part, where we could be using swarfing, because this is nothing but plain face, and we could run the tool as a swarfing tool. So what I have been swarfing, I have selected my geometry. I'll click on show. So I have got this entire edge as my swarfing geometry. Right. So let me run the calculation. And because it's automatic, I've just had selected the tool and the geometry to be swarfed, and it has done the swarfing. Let's see the result. Okay, that's the tool. It's going ahead around the periphery of the part. But look what happens when it reaches here. It's turned already, whereas it should have turned only on the radius out here. But what is happening is it's trying to maintain its axis to this edge of the swarf face. To maintain that, it's already started turning itself. And then it starts maintaining itself parallel to this edge out here. So let's move further. Yes. And as it comes to this side, there is another edge out here to which it is going to try and maintain its axis. So it's changing its axis gradually and then maintaining it to this side, and so on. And here it's doing a neat job again, because the axis here, again here, it's tilting itself in a very crazy way, all because it's trying to keep the tool oriented to the surface at every given point. Now I would like to control it. Like I showed you in the swarfing, I could create tilt lines like that. I could create about 8 different tilt lines, and I can ask software to maintain its tilt along this tilt line. So now it's already calculated with the new tilt lines. Let's see how it maintains itself. I'm more interested in the corners because that's where we had the problem. Okay, you can see that it's nicely maintained the tilt on the corners. Now as it traverses around the corner, this is where my angle change is happening. Right, again here, and turning around here, and it turns around here, goes to the end, turns around, retract. Now if I looked at this whole thing on a machine simulation perspective, you could see that it would make a major change in terms of traversing on the corners. So if I go step by step, I'd like to stop at the corners for you to see. And this is where I'm going to have the head moving around the corner. Travel again. Now because it's maintaining the tool axis with reference to the swarf surfaces, other than the tilt lines that I just defined, I could not be defining anything more than that. Because if I want to start controlling, for example, on a particular corner, if I've got a fixture that's holding it and I don't want the head to tilt that much down there, I want the head to tilt upwards, then I have a problem with swarfing. I cannot use swarfing. Then I need to go to another technique in SolidCAM, and that's called as contour 5-axis. In contour 5-axis, you have got an amazing amount of control that you can do with tilt lines. That's how it looked like in swarfing. So what happens in contour 5-axis? So if I'll switch on the tilt lines. For example, if I look here, I can provide tilt lines that are like that, which means it'll come straight, it'll orient itself here, it'll orient itself here, and the next position it will lift itself because I have some fixture out here which I don't want the tool to go and crash into. So I have oriented different tilt lines for it to orient itself. So I've got contour 5-axis. I don't need to define any surface in contour 5-axis. All I need is to define a drive curve and the tilt lines. Once I have done this, I have to hit simply save and calculate. And I would like to run this not in machine simulation, but in HostCAD so that you can look at how the orientation works. Sorry, let's go here. You can see that the tool is now maintaining its orientation as per the lines. As per the lines. And as it goes here, since I have another line here, it will try and maintain its orientation accordingly to that line at that particular point. And then move ahead, maintain the orientation with these lines, and go straight ahead. In spite of an edge being there, it's still maintaining its orientation along this line. Now look what happens out here. Within the span of this distance, small distance, the tool will now lift itself up because it has to orient itself around this line. So the user is now controlling its axis. He's not allowing the software to dictate to him how the axis should be, but he is controlling the axis. Now back again to this orientation out here. And as it comes to this line over here, you can see that it will orient again itself, orient to this line, move around, orient to the next line. So I am actually controlling how I want the tool to tilt. So if I have a fixture, if I have something that I want to avoid the collisions, then I'm going to lift that tilt line over there, and the tool will make sure that it will lift and follow the orientation of the lines that I've defined. So this is about Contour 5-axis. What we saw in today's presentation was we saw a few things. One was swarfing. We saw multi-blade, turbine blade, frame using swarfing. We saw trimming, and we saw engine codes. In our second series that's going to happen next week, we will see the other features like tire molds, fine features machining in die mold, 5-axis conversion, 3 to 5-axis conversion, super finishing of fillets using 5-axis and short tools, multi-axis drilling, STL machining, and if there are any other areas that I get upon in the coming week, that also will be shown. I'm now open to questions if you have any, and you can ask your questions. You can either type them in the chat, or you could just speak in your microphone. Raise your hand and speak in the microphone.
Okay, well, thank you very much for the presentation. I see there are a couple of questions. The first question is, when port machining, how does the software cope with bulges or undercuts inside the port?
How does the, okay. Let me open the port part. Oh, sorry, that's not the part. Open the video port. Right. So when I actually did this finishing, I'd like to show you more on the finishing. We've got an option here to gouge check. Now, in gouge check, I can define, first of all, by default, your gouge check against your machinable surfaces is already on. The second option out here is against the check surfaces. Now, this could be your undercut surfaces. So I can switch on the check surface, select against which check surface do you want to check the gouges. Unfortunately, on this port, I don't have an undercut, so I'm going to pick these surfaces, click OK, and simply hit calculate. I don't have to specify what it has to do when it detects a gouge. It's an internal built mechanism in the software that the moment there's a gouge, either it will tilt. The first reaction, of course, is to tilt away from the gouge. If the tilt fails internally, it's going to move the tool out of the undercut area in such a way that there is no gouge either with the cutting surface of the tool, that is the cutting part of the tool, or the shank of the tool. So it's going to move the entire thing out. The first is tilting. If tilting fails, it's going to move it completely out. I can simply hit calculate. I don't need to tell what reactions. That's the good thing about the new functionalities of SolidCAM, that most of the gouge checks, they are automatic. I simply have to just select the areas to be checked for gouge. There's another question that's asked, does 3D sketch tilt lines work with port machining and other strategies? With port machining, you don't need actually 3D sketch lines, but you can always define a spine. Now, this is in roughing. We have got an option to define a spine out here. A spine necessarily need not be a 2D sketch. It can also be a 3D sketch. But the extent of spine is basically left to the software. Now, if let me go to the tolerance. Now, if I push the tolerance up in port machining, let's say I go to point 1 and start calculating it. Or even more, with point 1 I don't think it will do it, but more than point 1, if I go beyond a certain tolerance, the software cannot calculate the spine automatically. In that case, we need to define the spine. It could be a 2D sketch or it could be a 3D sketch. Now, if you're talking of 3D sketch, then most of the lines that I showed you in the trimming, they're all 3D sketches. They were not 2D sketch at all. I mean, if you look at this line, it's a simple 3D sketch. One of these here. It's a 3D sketch. This was a 3D sketch. I edit this. This were all 3D sketches, and this was a 3D sketch. So they were not 2D sketches at all. I hope this answers your question. I mean, it does. It doesn't matter whether you're using a 2D sketch or a 3D sketch. For trimming, it doesn't matter. For port machining, we generally wouldn't recommend a 3D sketch, but it still does work with 3D sketches if it's within a tolerance.
Okay, well, Amon, thank you very much for this presentation. I hope you all enjoyed it, and we will see you next week for the second part of this webinar. Have a nice week, and we'll see you next week. Bye.